Let me know. Okay, so it's as you can see, so this is joint work with also with Peter and other people, Shira El-Kayam and Matthias and Steven Verheyen. And it came out of you know, Peter and Matthias have a paper in Journal of Mathematical Psychology, and also Matthias defended his PhD thesis, and Peter and I were in the committee, and so it was a discussion that came out of that. And so this is experimental work related to a theoretical proposal that they make in that article. Okay, so Peter already told you about conceptual spaces, and you may already have known about that. I also briefly reminding you of some of that. I'm going to talk about similarity-based inference and then Peter's and Matthias's proposal, and then the experiment we ran. And it's actually ongoing research, so at the moment we're still running an experiment, a follow-up experiment. We had hoped to have the results in already, but that's not the case. And so the idea is we're going to look at inferences that pre-theoretically seem warranted on the grounds of some kind of similarity holding between, you know, premises and conclusion, or concepts that occur in the premises and concept that occurs in the conclusion. And then the question is whether we can get a formal representation of that, whether we can formalize these inferences, and whether we can validate that the formalism that we have. Okay, so this is something that Peter already told you. So there's the classical logic, so the logic that we hear about, and you know, first year, our first logic course, and even also all later logic courses, at least at most philosophy departments and mathematics departments. So it's all, you focus on form, you know, and that makes logic powerful, because you can abstract from meanings, and you just look at form, and then you can say whether an argument is valid or not. So the meanings of the terms really don't matter, you know. So if I have this argument here, Alice is a philosophy professor, all philosophy professors are nice, and then we can conclude that Alice is nice. And the good thing is that just any argument that has this form is valid as well. But then we realize that there are some arguments that pre-theoretically are warranted, you know, are as warranted as this argument involving Alice. So when we say that that an object is blue all over, or let's say we start with the example, we say that an object is blue, then we can conclude that the object has a color. Or if we say that the object is blue all over, then we can infer that it is not red, not even a little bit red. And then, as Peter said, so Carnap had this idea of, well, okay, we cannot account for this in terms of form, but what if we supplement so this comes from outside the system, but now we take on board some meaning postulates, and then we get some relations between blue and being colored, and you know, between being blue all over and not being any other color. And then maybe we can save this, and we can incorporate it in our logic after all. But still, that doesn't, you know, that helps in this case. But then arguments remain, and there isn't this kind of solution available. So this is not the only example of that. But if we look at similarity-based inference, so then we find arguments where indeed it's, you know, adding meaning postulates is not going to help you. So if you if you look at this example, so where we suppose that you know a lot about cats, and for instance, you know that cats, as they get old, they tend to develop kidney problems. So almost all cats, if they're old enough, they develop kidney problems. And so now you from that knowledge you consider these propositions that dogs are prone to developing kidney problems when they get older, or elephants are prone to developing kidney problems when they get older. Now, so based on your knowledge about cats, and supposing you know nothing about dogs, or at least you know nothing about dogs in relation to kidney problems, or about elephants in relation to kidney problems, so what inference are you more likely to make? And probably, I guess this is not something we tested, but probably, so if you have cats and you know that cats are likely to develop kidney problems when they get older, you're much more likely to infer from that, or you will be much more confident to make the inference to dogs are prone to developing kidney problems when they become older than to make this inference involving elephants. I mean, it's not a certain, so you won't infer from what you know about cats with certainty that dogs will develop kidney problems, but you're more likely to, and you will make that inference with greater confidence. And the idea is probably that is because dogs are more similar to cats than elephants are similar to cats. And so this is this kind of inference in the psychological literature. It's called category-based induction. And so in philosophy, it's typically called analogical inference. So the structure of the form of this is so you have a premise which says that all x's have some property p, and then the conclusion tells you that all y's have some property p, and then the data that already exist suggests that the more similar people think y's are to x's, the more likely they are to make this inference, to agree with the conclusion. So that is already known, and it has been tested over and over again. And then, so psychologists won't be so worried about that, but for philosophers, they are typically only satisfied when they can formalize inference, at least well as far as possible. And then here the worry is that if it relies on similarity, then, well, similarity in the philosophical literature has a bad name, since Nelson Goodman made these, and some philosophers are familiar with Tversky's work, and so they think, no, similarity is a fake notion, and we don't really understand what we mean by that. So it would be really unfortunate if we had to rely on that notion in a theory of analogical inference. But then, of course, so there is now, in the past 20 years or so, there is this work which Peter initiated in his 2000 book. I mean, that brought it together, that built a framework, and that actually showed that there was a framework, and I had been work in cognitive psychology already beginning in the 1960s. So if you look at Shepard's work and then later Nosovsky's work, so even though at the time it wasn't realized that there was this common framework, but people had started to analyze this notion of similarity in very formal mathematical terms, so basically in geometrical terms. And so then the conclusion to draw from that is that no, similarity is not a fake notion. It's actually a very precise notion. We can understand it using mathematical tools, namely spaces. Okay, now you heard already a bit about conceptual spaces, or more than a bit. And so the idea is that these are so one-dimensional or can have more dimensions. The idea is that you can map objects, items onto points in these spaces, and these dimensions somehow correspond to very fundamental qualities in terms of which we may compare objects to each other. And so where do these qualities come from? Well, they can very often be related to parts of the perceptual apparatus. So for instance, in color space, Peter showed this, you had this, you had the color circle, and then you had the intensity or saturation, and that was the brightness dimension from top to bottom, from black to white. And people have been able to really to link these dimensions to parts of the perceptual apparatus. So what we use, the eye and the brain, all that is involved in color perception. And the idea, as Peter already said, is that these spaces, so by distances in those spaces, you represent dissimilarities. So meaning that if two objects or the representations of two objects are further apart in these spaces, that means they are more dissimilar, or the other way around. The closer they are, the more similar they are. And most of the ones that we have, there are not so many that we have in the psychological literature, but we have a number of them. And so most of them have been constructed using some statistical technique. Very often it's multidimensional scaling, principal component analysis, or related techniques, non-negative matrix factorization. And so you start then, at least this is the normal procedure, with similarity judgments. You have many, many similarity judgments. For instance, you show people pairs of colors, so take just, let's say I have color patches, I have many color patches. I show them two color patches, and I ask them how similar are these, shades of color, and then they can respond on some scale, maybe from 0 to 100. I don't know. You do that for many, many pairs, and then you can use this technique, or you can use something else. You can flash two colors very quickly after each other, and then you can ask people, are they the same or are they different? And then you look at the rates at which people confuse, if they say they are the same or in fact they are different. Okay, then that's a mistake, and you measure it, how likely they are making mistakes. And there are other kind of data that you can use, and you use that as input for these techniques, multidimensional scaling, and then what you get in return is some space. Hopefully it's two-dimensional, because that's you can represent that nicely. Maybe it's three-dimensional is also very good. If it's five-dimensional, that's not so good. That's not what you want, actually, because it's, I mean, if that's the best fit that you can get, then okay, you have to work with that. But it's better if you have a two or three-dimensional model. And then you have to see whether that model is so good, so you measure this in terms of stress. So maybe, it's like model fit. So this gives you kind of a model fit. So is the geometrical model that you get out of the statistics, is it a good model fit? And if so, then you can work with that. And so we have a number of these models, as I said, not very many, but we have a number of them which we can work with. So here I give some examples, but so color space, which Peter already showed, that's the best known one. There's also olfactory space, that's maybe 5 years ago, or maybe already 10 years ago, but that was published. The other ones that you can find in the psychological literature, so some shape spaces and action spaces, event spaces, there's a phase space. People have been working on moral space, in which they can represent moral concepts. And then, of course, these are, it's important to understand that these are just similarity spaces so far, you know, so you need to populate them with concepts to make them conceptual spaces. But so far we don't have conceptual spaces. These are just similarity spaces. And I tell you a bit about how you can get these concepts into these similarity spaces. So a bit of basically prehistory and how we are going to use them and how people already thought about how you can use these conceptual spaces. So assume you have a similarity space, you can populate them in some way with concepts. So there are many ways to do that. And so if you look in the old literature, so Carnap had been working on non-deductive inference, so also, let's say, analogical inference for all his life almost. And he was never satisfied. But he kept working on it, which is something to be admired. But then only, you know, at the end of his life, he thought, okay, no, this is not going to work. So the purely syntactical approach that I would want to succeed. So the idea was, can we have something like deductive logic, but now for analogical inference, for inductive inference, maybe other types of non-deductive inference. And he kept working on that. And then at the end of his life, and it wasn't even published, it was published posthumously in 1980. And Carnap died in the 1970s, you know, I forgot when, maybe 1971 or so. And only then he gave up this idea and he said, no, this is not going to work. So we are not going to have inductive logic that is purely syntax based, so that really parallels deductive logic. So we need to appeal to semantics. And then the way he did it was he came up with an idea which he called attribute spaces. And so at the time he didn't have a real understanding of what these attribute spaces had to look like. But if you read that you know, this posthumously published work, then you will see they go in the direction of conceptual spaces. So that was already, he doesn't refer to Shepard's work, but it existed at the time already. Shepard had started working on this in psychology. And so you see that he already had this, he had heard of it. So there is a footnote in which he refers to work being done in psychology, which suggests that he knew something about the work that Shepard was doing, or maybe other people were doing also that kind of work, but maybe these other people didn't publish their work, or they got forgotten. In any case, I suppose he knew something about Shepard's work. Also in the 1960s, Robert Stolnaker and Van Fraassen were also referring to using semantics in modeling inference. And they also were thinking about spaces. But unlike Carnap, they had no idea of what these spaces had to look like. But they just draw these spaces, assuming that one day we will have such spaces. They don't look like real conceptual spaces. But in any case, it's nice to see that people were thinking about, if we want to formalize non-deductive inference, we need to refer to some kind of spaces. And then it's only so Peter, of course, developed this framework of conceptual spaces. And then it's only in this paper by Matthias and Peter in which they use these spaces to come up with a proposal for how to formalize analogical reasoning in conceptual spaces. So that's basically formalize category-based inductions in conceptual spaces. So that was a lot of work in psychology on category-based inductions, but it was non-formal. It was purely informal. So just use people's judgments about similarity, and then see whether you can make predictions based on that about the inferences the analogical inferences that people are willing to make. Now, so this was This was the proposal that Matthias and Peter come up with in their paper. And so I think the one thing to remember is, they make it formally precise in terms of expectations. Peter already talked about that, so it's related to the other work that they were doing. For now, that's not so important. The important ingredients are, so if we look at these similarity-based arguments, so then inference strength depends on three things: premise conclusion similarity. So there's I explain more: a premise typicality and conclusion typicality. So if you think of this inference, so we have a premise and it says that so X, all X's have property S, and then the conclusion is all Y's have property S. Then it depends on how similar are X and Y, where these actually, so this is, how likely, how happy are we to transfer, so to speak, this property S from knowing that X's have it to Y's. And the idea is that X and Y both fall under a more encompassing property. So for instance, X could be cats, Y could be dogs. They fall under the more encompassing property of being mammals or animals, depends a bit on how widely you want to take the space. And so then the idea is, well, it depends on how similar they are. And it depends on how close dogs are to the prototype, to prototypical animal or mammal, whatever your space is, and how typical, how typical cats are to the prototypical mammal, how typical dogs are to the prototypical mammal. And then the idea, so we have these three components, and so it's a weighted sum, right? I mean, and so I think then the suggestion would be normally you want to estimate these weights from the data, and they might be different for different domains. Now, there was already some work, so this is not the first research we did on this. So with Peter and also some other people, we already worked on analogical inference. Actually, we found that these factors didn't contribute actually so much. So the main focus is on the similarity between here these concepts mentioned in the premise and in the conclusion. And so what Peter and Matthias do in their paper, so they have some illustrations and they have some spaces. So they use bird space, they use mammal space, but as they say, look, so these are illustrations. We come up with these spaces, we draw these spaces, but they have not been empirically validated. They don't come from the psychological literature, so these spaces, as I said, I mean, these just serve illustrative purposes, which is good because it's, you need these kind of illustrations. But of course, the question was still, can we test this proposal using real spaces? It's clear that it is testable, so it makes clear empirical predictions. But you need a real space to test it, and you can't do it just on the basis of spaces that you draw and that you think, well, maybe this, you can draw a mammal space and it can look plausible, but that doesn't mean that if you test it and you gather data, that it will be validated by those data. Okay, so we needed some kind of space to test our proposal. So that's what we set out to do. And so we wanted to do that by constructing a mammal space and then use that mammal space to predict inference strength of category-based inductive inferences. And as I said, we had this previous research which suggested that the prototypical information was not very helpful. that I'll tell you a bit about why this may depend on the space that you use. I mean, maybe here it's not very helpful. Maybe if you can come up with a better space, maybe it will be helpful, but here it wasn't. And so then this was a hypothesis that we wanted to test, so that the strength of category-based inductive inferences is a function of premise conclusion similarity. So there was a concept mentioned in the premise, a different concept mentioned in the conclusion, and then some property is attributed to both. How happy are we to make that inference? That depends on how similar these concepts are. So if we know how similar these concepts are in the perception of a participant, so let's say we have a space, and then we can measure the distance between them in the space. Then we can predict. That's the claim. That's the claim of the hypothesis. Then we can claim how happy the participant is to move from all y's have property P to all x's have property P. So for some given property P. So then for that we need a space, and we need then data about perceived inference strength. So that is what we then did. So that is what the experiment was meant to accomplish. So that one thing to do is get data so that we can build per participant a MAML space. So for your MAML space might be different from my MAML space. I mean, that's even known even for color space. If you Google so color similarity space, that's not a color space in your computer. So that's not RGB space. That's not color similarity space. That doesn't give you similarity judgments between color shades. But if you Google CLab space or CLOV space, these are color similarity spaces. And so now we needed something similar for MAMLs. So there you can use distances in those spaces, which should really, if it works, if you get a good space, which should predict similarity judgments. But it is known already for color spaces. So even though we have the CLOV space and CLab space, they do represent human similarity judgments. But if you look at there are individual differences, so they are a kind of a good average. But for different people, different people have different color similarity spaces. So my color perception is a bit different from yours, which can have to do with differences in our eyes and how the brain works, maybe education, how we have been trained to use colors. Okay, so we wanted to have a MAML space per participant. And then we can, from that, also have a kind of aggregate space, so kind of average. We can do that, but first we need the individual spaces. And then we use those to try to predict that participant, so per participant, the judgments of inference strength. We made use, for the materials, we made use from older work from Henley, who had worked on MAML space. And we selected 20 MAMLs at random, just no reason why we use those, but we needed just 20. You can have 100, but you will see the task that people had to complete. That was with 100, that would have been way too difficult. With 20, it's already not so easy, much more difficult than you would guess. I'll show you the task. And so what you can do is, I told you that sometimes, or very often, you create these conceptual spaces using multidimensional scaling or principal component analysis, and then you need pairwise judgments. So you could have 20 MAMLs and then elicit pairwise judgments. So let's say I tell you, so here I have cat and dog, how similar are they? Here I have cat and donkey, how similar are they? Here I have chimpanzee and duck, how similar are they? And I do that for every pair. That's a lot. I think that's close to 200 similarity judgments. If you want to do that for all participants, that's actually that's going to take quite some time, and you have to, well, typically you have to pay participants. Here we didn't pay them. Here they were students from the University of Rotterdam, Erasmus University. But here you give them credits, and you're not allowed to give them tasks which take more than 20 minutes or so. So, and then this would take much longer. So we used something else that has been recently developed, or at least that has been recently made available for online use. So we use, and many people use now for running experiments. This was already pre-pandemic. You can run experiments online, and there was a very good platform for that, Qualtrics. And Qualtrics recently, a year ago or so, they added a functionality to run visual arrangement tasks. And so what you do here, I'll show you the task. And so this is what they saw. So we told them, so you're going to see 20 animals on screen. So just the names, names of the animals. And you can drag and drop them, and you can put them anywhere on the screen where you want. And the task is actually you should use the whole screen, and but then do it such that if the more similar you think two animals are, the closer together you place them on the screen, and the more dissimilar are, the further apart you place them. We gave them an example. So suppose we have 5 items: an apple, pear, carrot, spinach, lettuce. Then this might be this is just an example of something that you could come up with. You place them in some order, you find some placement of these 5 words on the screen, which reflect your similarity judgments, which might be this or which might be different, but then I guess this is how it might look like. Now, this is probably a bit too small, you can't see this, but so this is what they saw. But big enough. And so these are 2 columns, so 20 names of 20 rectangles, each of them containing a name of a mammal, so tiger, wolf, giraffe, gorilla, and so on. And so they could drag each of these rectangles, and they placed them in some, wherever they wanted to place them. And so the absolute placement didn't matter, but what mattered, of course, was how close they placed things together and how they grouped these things. And then there was a second part of the experiment, in which they had to answer questions about inference strength. And so they were given 30 questions. And so every time they were told that a certain class of animals has a given property, and then we had a conclusion that a different class of animals had that property. And then we asked them, well, how strongly do you agree with that? How strongly do you agree that conclusion follows from the premise? So that's how we measured inference strength. And it looked like this. It looked exactly like this. This is a screenshot. So this is what they saw. This is one example. So this is an example involving zebras and cats. The property was always specified abstractly. This is one of the 2 paradigms in the psychological literature for this kind of work, for category-based induction. So one way to do it is use abstract properties. It's not ideal, but nevertheless, at least that way you don't introduce a confound. Another paradigm is you use made-up properties. It's like, suppose zebras have sesamoid bones or something that is basically meaningless to participants, or that is done as well. It's also not ideal. It's just, that's the best that people have been able to come up with. And then there was a slider, and they could place a slider wherever they wanted, so follows very strongly, or does not follow at all, or any place in between. So this was the second part of the experiment. Now, so here you see, so the software, this Qualtrics software, this gave us the coordinates on their screen. Of course, people had different screens, the sizes of their screens differ. And so Qualtrics also gives you those sizes. So you can rescale them so that you get you can represent them in a unit square. So here, for instance, participant number 1. I mean, the numbering is of course arbitrary. This is what that participant came up with. So this is really how he or she placed these 20 rectangles on the screen. And of course, you can see it for all the other participants as well. There's a second participant. This the third participant came up with. The fourth participant. For each participant, you have these results. And you see, we had asked them, please use the whole screen. Not all of them did that. Of course, these were students. Some students are serious. Some are. There are always some students who don't take the task so seriously. That not much you can do about that. But in any case, we had now per participant mammal spaces. And then what you can do is so we also had per participant responses to these inference strength questions. So they had these judgments. And so now the question is, and that was the question that was suggested by our hypothesis, can we predict on the basis of these per participant mammal spaces, can we predict the strength of the inferences, from these, if cats have property M4, then dogs have property M4, or then zebras have property M4. And so the prediction is that, let's say, if the premise is if cats have a property, sorry, if cats have property M4, and then if participants judge dogs to be very similar to cats, and then we have if dogs have property M4, they are much more likely to say yes, that follows from the premise than if, say, if elephants have property M4, while these elephants are not so similar. But I mean here more precisely, really the distance. So this is something that a quantitative prediction. Exactly the distance in this mammal space for that participant. That is going to give us. This is going to give us exactly the strength. So this, exactly. This is going to predict, so to speak, the placement on the slider that you saw for that participant. And okay, we have to see whether that's true. So whether, are we going to have linear regressions or some other type of nonlinear regressions? Yeah, I mean, if you plot, let's say the data, it does, it suggests, let's go with linear regressions. Later on you can try something else. I mean, it does look a bit that's maybe the best thing to start with. So here we fit the linear regressions. Now only look at, so this is the predictor that we have. That's this DST, which stands for distance. And our response variable was inference strength. And the only thing actually that we want to know is, so the only thing to pay attention to is this a significant predictor? Can we significantly predict from these measurements in the participants' mammal space, can we predict the judgments of inference strength? And the things to look at is, so this value, so is it significant? So you saw this is participant 1. So yes, it's highly significant, for 0.0004. And also look at the coefficient. So it's negative. So it means as the distance gets bigger, the inference strength gets smaller. That's what it says. And that's also what you want, right? I mean, greater distance means less similar, more dissimilar. So that's what we expect. That's what our hypothesis says. So, the inference strength gets less. So inference strength diminishes as distance in the mammal space gets bigger. And you can do this per participant. We did it per participant. Here again, look, highly significant, negative coefficient. So, we run these regressions per participant. You see highly significant, negative coefficient. same, 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 same. Okay, so at least this is looking good, right? I mean, now let's look at the p-values. You know, again, I mean, if you look at, so let's say we have an alpha level of 0.05, so, and then you see that for 83% of the participants, this predictor was significant at that alpha level. Even if we go, let's say we have an alpha level of 0.01, it's still for about 70% of the participants, it was significant. And if you plot the p-values, then you see, you know, for the vast majority, it's a really very low p-value, so to speak, so highly significant for most. So that means for almost all participants, distance in this mammal space, in their mammal space, and their representation of how similar these mammals are to each other, that predicts how likely they are going to agree with this inference, where you go from, you know, some attribution of a property to a mammal to that the other mammal, you know, that is in the similarity relation. We can plot the individual models, and then you basically see that you get what we expect. So here is the inference strength, and you see as the distance gets bigger and bigger and bigger, then the inference strength, you know, they're less and less and less likely to agree that the conclusion follows from the premise. Again, as I said, this is what you expect. Now, you can also, on the basis of all the individual spaces, you can create an aggregate space, right? I mean, it's like, as I said, you do the average. You can't, given that absolute placement didn't mean anything. So it doesn't mean anything whether a participant puts a tiger here or puts tiger there. That doesn't mean anything. It's all about relative, you know, placement. So about the distances between tiger, lion, tiger, cat. You know, so then what you can do is you can just measure all these distances, you average over the distances, and then you use the classical multidimensional scaling, and then you create an average mammal space. There was something really interesting about this. So this is the average. Let's say this is the average person's mammal space. And there was something interesting about this, because when we, let's say, pre-tested this experiment before we ran it, so Peter and Matthias and Steven and Shira and I, we all went through the experiment. That's what you normally do a couple of times, just to see whether, you know, you see something which might confuse participants. So it's like you are a participant and you take the experiment a couple of times. And in this task, so we found, in this visual arrangement task, we found that it's actually not so easy, because you would think it's easy. I mean, it's easy, of course, to move these things around, but it's not so easy to place them in a completely satisfactory manner, so that you know, if you do it just locally, that's not so difficult. So yeah, okay, we all agree that you can place cat and tiger and lion close to each other, and you know that's not a problem. But still, I mean, you know, to make sure that the whole picture makes sense, so to speak, that it represents your similarity and dissimilarity relations, that's really not so easy. And so when you do this, you know, you may spend 1 or maybe 2 minutes on that, but you're not going to spend 5 minutes on that. And I'm pretty sure that the students spent even less time on that. So whenever we went through the experiment, we were never completely satisfied, but we were just satisfied enough to move on. The nice thing is that when we saw that in the aggregate space, we all had the feeling, oh gosh, this is actually better than not just than what each of the students came up with, but what each of us came up with. I mean, if you look at this, then you think this is actually a very, very nice space. So this suggests something like, you may have heard of this idea, you know, the wisdom of the crowds. So that somehow the aggregate judgment is, at least very often, is better than individual judgment. And they tested this, and it turns out that aggregate judgments, even of random people, in some contexts, are better than even expert judgments. So, I mean, there's famous research on cattle markets where they ask random people to estimate the weight of a pig that is being sold. And then they take the average of these judgments, and it's very close to the real weight of the pig. And can be closer to the weight of the pig than, if you have an expert, someone who weighs pigs a lot because that's his job or so. And even so, the average judgment is closer to the real weight of the pig than the expert's judgment. It's very fun. But in any case, this suggests that you have something like this wisdom of the crowd effect also at the conceptual level. And that dovetails nicely with an idea that Peter had in his 2014 book, in which he basically advances the idea that, so even though there was famously, Putnam claimed that, meanings are not in the head, and then what Peter actually argues in his book is that is true, that Putnam was right, or it's not really in contrast to judgment, but to Putnam, but that's a useful way to think of it. And so what Peter argues that, well, think of it as meanings having a social aspect, so meanings are in the heads. And that's basically what you could think of the result that we got in that manner, that the concepts, so the real concepts are represented by this aggregate space. So it's not in any one of our heads, but it's a social thing. It's in our heads, so to speak. And I think that's very nice. And this could also, we haven't done that, but this could also be empirically validated, because this is now just our judgment. But we could do this with a number of spaces and then see whether people agree with that. There are ways to do that. Now, I see I'm running a little bit out of time. So you can use then that aggregate space again to rerun the linear regressions. And in fact, you get even better results. So now you see that at an alpha level of 0.05, 95% of the participants, for them, so distance in that aggregate space, aggregate mammal space, is a predictor of, is a highly significant predictor of inference strength. Good. Again, you can plot the models. Okay, so now, I'm now done. Sorry for taking so long. So these are the main findings. So we find that the distance in personal mammal space, they tend to be, not for all participants, but for most participants, almost all participants, a highly significant predictor for these category-based inductive inferences involving these mammals that we had represented in that space. And then we see that the distances in that aggregate space are even better in this regard. And then, as I said, we are now running a follow-up experiment. That is just about inference strength. We rerun this inference strength part of the experiment, and now we have more questions to have greater power, and also to be sure that we don't have any carryover effects. And that's really just because we were so happy about the results from the first experiment that we thought, okay, we need to make sure that, absolutely no complaints can be raised about this, and no referee should complain about this, and we do this follow-up experiment. And well, if we get here the results we hope for, then I think this is a good validation of Peter and Matthias' proposal, and more generally this idea that you can use conceptual spaces to represent analogical inference. Okay, so thank you. That was all.